Hello, everybody. My name is Ethan Foss. Today, I'll be presenting on a stellar observation scheduling scheme for distributed space interferometry mission. This is work in collaboration with Antonio Rizza and Simone D'Amico as part of the Space Rendezvous Lab at Stanford University. So let's start with a little bit of background. Obviously, exoplanet detection for detecting signatures of life in extrasolar systems has become a very popular topic in astronomy and has led to the development of several flagship missions like the James Webb Space Telescope and the Habitable Worlds Observatory. But despite the number of missions and Earth-based techniques for characterizing exoplanets, there exists a fundamental limitation to characterizing the atmospheres of Earth-like exoplanets, which are ultimately the systems that we expect to see life in. So as a result, increasing emphasis has been put on distributed space nulling interferometry concepts, which involves multiple distributed satellites reflecting and combining light to reconstruct exoplanet atmospheres. So in this light, there have been several missions that have been proposed for addressing this issue. So this includes NASA Terrestrial Planet Finder and ESA's Darwin missions, which unfortunately never saw space. However, recently a new mission known as LIFE has been proposed and is leading to renewed interest in these concepts. However, because of the severe technology requirements that are needed to realize a mission like LIFE, there have been several low-cost LEO-based interferometry missions that have been proposed to demonstrate the key technologies for LIFE. So this includes Sylvia from JAXA, Stereos from University of Tokyo, and Starry from NASA and University of Michigan. However, there still is a gap here, and that is the question we pose in this work, which is how can we quantify the scientific potential of these missions? And in addition, how can we maximize the possible scientific acquisition of these missions? And so towards this goal, we pose the problem as a coupled trajectory optimization and scientific reward scheme. So basically what we propose to do is simultaneously optimize relative motion trajectories and stellar observation paths. Although similar multi-objective optimization schemes are often studied for mission designs, popularly in interplanetary trajectory design, the one proposed here is unique in that it represents one of the first applications to low Earth orbit interferometry concepts. So with this in mind, let's go into a little bit of background about LEO interferometry and explain some of the relative orbit concepts that are needed to realize these distributed space systems. The key driving requirement for realizing these designs comes from something we call the optical path difference. So in these concepts, we seek to have two or more collector spacecraft that reflect incoming starlight to a central combiner spacecraft. And what the optical path difference describes is the difference in distance that the starlight travels when the two light paths interfere at the combiner spacecraft. This is really necessary for achieving that deep null, basically deconstructively interfering the light so that the starlight gets suppressed and the Earth atmosphere spectrum gets magnified. So it turns out there exists one general family of solutions to the linearized equations of motion of Keplerian motion that allow for natural motion with theoretically continuous zero optical path difference. These formations were originally discovered by someone named Jonah Hansen, and these are known as linear formations and involve spacecraft on either side of a central combiner spacecraft oscillating in the normal direction of the orbital motion plane. These formations are such that the relative orbital motion plane is perpendicular to an inertial target for the entire duration of the relative motion. The other thing that's important to note here is that we can arbitrarily increase the separation of the spacecraft from the combiner. This is known as the baseline length. And it basically allows us to exploit different spectrums when observing a given stellar system. So to proceed further, I'm just going to briefly introduce some relative orbital element definitions. These are, in particular, quasi-non-singular relative orbital elements, which will prove to be useful for our further analysis. And basically, what these relative orbital elements do is they represent the motion of the spacecraft as integration constants. So now the state representation of any given spacecraft is stationary in time. Um, and as we see, the relative orbital elements, when we look at the distributed interferometry formation that we're interested in, we see that they encode a lot of useful geometric parameters in terms of some of the stellar angles, or basically the angles formed of the stellar target onto the orbital plane. One thing that's also really important to note for these solutions is that they lack this notion of what we call passive safety and relative motion design. And basically, what that means is for different science orbits, we have to intermediately transition between standby and science orbits. So basically, if we have one science orbit and then we have another one planned in the future, we have to go to a standby orbit between that observation. So we can see in this animation here, basically all that's going on is we're transferring back and forth between a standby orbit, which is the circular orbit, and the science orbits where we actually perform observations of a stellar system. Another thing that's really important to note as well is that there are several constraints that basically inform the regions of the celestial sphere or the stellar targets that we can and cannot observe. So the first one that's important is sun exclusion. This basically enforces that any observation be excluded from oncoming sunlight to within a certain angle. This is done to protect, the scientific sensors and ensure good measurements. And what this constraint basically forms is a vector pointing away from the sun has a cone of stellar targets that we can observe. The second constraint is Earth occlusion. And this basically constrains the duration or duty cycle of an orbit for which we can observe a stellar target. So you can imagine if you have a stellar target that's coincident with your orbital plane, your Earth is going to be occluding that target around half of the time. Whereas if you have a stellar target that's pointing normal to your orbital plane, you can see that pretty much all of the time. The last constraint that's important comes from the relative motion itself. This is a constraint on the baseline oscillation. So there's angles with respect to the normal of the orbital plane for which we can observe a stellar target based on how much we can allow the formation to oscillate in the normal direction. So if we just take a quick look at what this forms in the celestial sphere, we can see how the observable regions are affected. So this is a specific instance of a sun-synchronous terminator orbit. What we'll see is that we're going to be studying sun-synchronous orbits because they basically allow for theoretically continuous observability of the celestial sphere. And we can see as a result of the precession of the absolute orbit over time, the observable regions of the night sky rotate across the celestial sphere over the course of a year. And here we have the observable regions colored by the duty cycle or percentage of time of the orbit for which we can observe a given stellar target. Another interesting thing to note here is that we can view these observable targets in the inclination vector plane. Basically, what this amounts to is stellar targets traveling across the inclination vector plane from right to left in like a hyperbolic trajectory. It's also important to note that any mission is going to be constrained by fuel expenditure, so not all stellar observations are going to be equal in that sense. And so we can incorporate this using our relative orbital element definitions, basically as the distance traveled over the relative inclination and relative eccentricity vectors to quantify the cost of transferring to a new stellar target. In addition, we can quantify station keeping cost of a scientific orbit in terms of a simple empirical description. Lastly, it's important to consider how we actually quantify the scientific reward associated with observing a stellar system. I won't go into too much detail here, but the metric we use is known as yield, which basically describes the expected number of exoplanets that will be detected given the observation of a given stellar system. We use stellar target data derived from the Habitable Worlds Observatory catalog. So with this in mind, let's now present our problem. Basically, what we want to do is, given some set of feasible star paths or observation paths, we seek to find the observation path that satisfies our constraints and maximizes our scientific reward. And this will give us our associated relative motion trajectories. To pose this problem concretely, basically, we want to maximize expected exoplanet detections weighted by the duration of time for which we can observe them, subject to emission fuel constraints and a constraint on the time between observations. So we enforce that we need to do observations between a cadence of 1 to 2 weeks. The key insight that we can make here, though, is that we can reframe this problem as, instead of a single objective optimization problem, a multi-objective optimization problem. So instead of just optimizing scientific reward, we're simultaneously optimizing scientific reward and fuel expenditure. This allows us to explore the trade space a little bit more. And now our optimal value is not just a singular value, but it's a set of values on a Pareto front associated with a set of Pareto optimal paths. And we can use the important insight of dynamic programming, defining our value function as this Pareto front, to compute Pareto optimal solutions using a recursive Bellman update. So let's take a look at some results here. So on the top left, we have the Pareto front associated with a solution for a low Earth orbit interferometry mission over the span of 6 months. And we see on this Pareto front, obviously, we see that increasing scientific reward, it requires increasing delta V expenditure, as we'd expect. And we can see on the top right figures the associated paths that the interferometer takes to measure stellar targets on the celestial sphere. On the bottom here, we have plots associated with the relative motion trajectories in the relative inclination and delta A, delta lambda plane, along with the RTN relative positions of the formation. And I will show here the trajectories of 3 points on the Pareto front. So this first trajectory that we have shown here is the high reward, high fuel expenditure solution. And you'll notice as we move to the medium reward, medium fuel solution, we see that the relative motion kind of grows closer to the origin. This is associated with lower cost station keeping orbits. And as we move to the lowest fuel, lowest cost solution, we see the relative motion moves even closer to the origin, decreasing fuel expenditure even more. Finally, we have these additional test cases to show the variability that the scheme can handle. So here we have different orbits of interest, including 500 kilometer, 1,000 kilometer, and 1,500 kilometer orbits. And we've demonstrated them on 2 different types of sun-synchronous orbit. So one is a terminator orbit. This is the situation we've been considering so far. And on the right side, we have the nude midnight orbits. These ones are slightly different in the sense that now we can only perform observations of the celestial sphere when the sun is occluded by the Earth. And basically what that means is we can observe either portion of the celestial sphere. And this is something that our optimization scheme actually leverages. You can see there are 2 sections of the celestial sphere that move across the celestial sphere over time. And our optimization scheme is basically coming up with paths that switch in between these 2 regions to maximize the associated scientific reward. Lastly, we have a plot of the Pareto fronts associated with each of these cases, which give a quantitative assessment of the effect of different absolute orbits on the scientific potential and fuel expenditure of our associated mission. So in conclusion, our contributions included a multi-objective dynamic programming scheme for distributed space interferometry. This scheme is not only useful for stellar observation scheduling of these missions, but as a tool for mission designers seeking to explore different trade spaces and as a means of assessing the scientific potential of these mission concepts. In the future, we foresee work involving expanding to eccentric and Sun-Earth L2 orbits, which are the orbits we expect to see very advanced nulling interferometry missions take place, and demonstrating this mission design tool on a real mission. With that, I'll take any questions. Thank you very much.